We've been looking at some diagrams like this heating curve and also phase diagrams. And I want to take you now to start to think about where these temperatures come from and if we can predict them. So water has a relatively high boiling point, but why? To understand that, we need to go back to something that we learned before, and that is that molecules are polar. So I'm going to go back to our Chapter 8 material to talk about polarity and see how, if we can work our way to polarity, then we can understand intermolecular forces. This is our new piece in Chapter 10. And then we can also from there talk about things like melting and boiling point, or surface tension and viscosity. So let's take a quick minute to review here. We learned in Chapter 8 how to draw Lewis structures, how to put our molecules into the right shape, like this bent shape. And you can see you want to keep everything you've learned at the front of your mind. Then we talked about being able to draw bond dipoles. Anywhere there was a polar bond. Remember, C's and H's share electrons really evenly. They're kind of like twins, so there's no bond dipoles there. And then we can draw our molecular dipoles. And remember, if I have a molecular dipole, it means the molecule's polar. And so then I would say this CH4 over here is nonpolar in comparison to the two polar molecules here. From that polarity, I can start to predict inter, or between molecules, what kind of attractions I have. And so this new term that we're using here, intermolecular forces, is going to be these attractions that are weaker than a bond, but still kind of like Velcro, strong enough to hold things together, not necessarily a screw or a nail, but able to hold things together like Velcro. So we're going to see intermolecular forces that look like this, or if I take this CH3F molecule and I look at how it would align with its dipoles, the dipoles would line up end to end. Those would be held together by intermolecular forces as well, kind of that molecular Velcro. And then the CH4s even, they could have just a tiny bit of that intermolecular force attraction. I'm just going to draw a couple of little lines, and notice I tend towards vertical instead of horizontal because they're easier to see like that. So these intermolecular forces then impact my boiling points. If I look here, I have a relatively high boiling point, and then a lower boiling point, and then the lowest boiling point. That means that this is relatively hard to boil. That's why it's a liquid still at room temperature. If it's hard to boil, that tells me that I have relatively strong intermolecular forces. These are hard to pull apart, hard to boil. Next one, this is easier to boil. Obviously, this is actually gas at room temperature. And so I have weaker intermolecular forces. Those are connections we're going to be making throughout this chapter. And then if I have a gas here, that's the easiest, or this gas is the easiest to boil. And you can see that because it boils all the way at negative 162 degrees. And so this has the weakest IMFs of all of these. So being able to look at intermolecular forces, these little attractions here between molecules, allows us to predict what's going to happen with our boiling points. So in order to work with these, you have to be able to figure out, is something polar, and then what kind of attractions do I have, and then you can predict what the boiling point is. So we're going to look at now a couple of quick examples of where these show up in nature, and then we'll look at the different types of intermolecular forces. So I'm always curious, like, who cares? Why do I care? Where do these show up in nature? So just a couple quick examples for you. Intermolecular forces are pretty awesome. Once you know to look for them, you find out that they really are important in lots of different areas of life. So these intermolecular forces aren't bonds. They're maybe like 10% of the strength of bonds, but this is what would hold ice together. Or there's some intermolecular forces holding water as a liquid, keeping those particles relatively close, like we saw earlier. If in a bio class you've ever seen a substrate that gets held by an enzyme, this would be like lactose in your milk and then lactase enzyme. You don't want them to be stuck together forever, so you want this kind of molecular Velcro, the intermolecular forces, that would hold the two things together and then let them go. So you want it to be able to be temporary. Another place that these show up in nature is holding DNA together. So if you remember from a life science class, DNA has to separate every time you replicate it, or if you are copying a gene to go express a protein. And so we have intermolecular forces in between, so this would be right here through the middle of DNA. We want basically Velcro, so we can open it up and then we can close it. So we want something that's rather temporary to hold those together. So those are a couple of places, holding our solids together, holding enzymes together, holding DNA together, a couple of places where we see intermolecular forces in nature. So what are these intermolecular forces? Let's take a look at 4 different types of intermolecular forces. And a lot of the description for them is right in the name, so utilize that in helping you learn these and figure out what's happening. All right, so we're going to look here relatively from weak IMFs up to stronger intermolecular forces, and we're going to look again at 4 different types. Let's start with the weakest ones, and the weakest ones you'll see described with about 4 different names. Induced dipole, induced dipole. That means kind of like it's an accident or it's temporary. London dispersion forces, or just dispersion forces, or even van der Waals attractions. Van der Waals can also be described being all 4 of these. So we're going to look on this table at who's involved. Here's some definitions, and then I'll give you an example. So for dispersion forces, we're thinking about on all of these intermolecular forces. These intermolecular forces are attractions, right? And if you can remember back, one of our key principles for this class is that opposites attract, right? And so we're going to see that positives and negatives end up attracting each other in these intermolecular forces. So here with these induced dipoles, these are just kind of accidental collisions. You could think of them as accidental quick conversations like you might have with someone in the hall or at the mall or a park if you weren't all in quarantine. So this would be all of our molecules can participate in these accidental quick conversations or quick attractions. But they're especially important, so especially important for our nonpolar molecules, and we'll see why as we progress through this table here. So especially important for nonpolar molecules. So what are these? They're going to be due to temporary changes in electron density. The bigger the molecule, the more chance of a temporary attraction. And so essentially this is just, say I take 2 CH4 molecules and they bump into each other, then they create their own temporary opposites attract situation. So the big bulge here would be, I'm going to use a lowercase delta, partial negative, and that would be where the electrons would temporarily hang out. And then I'm going to have a partial positive here just from colliding. After the collision, each of those CH4s will go back to just its nice round cyclical electron cloud. But this temporary attraction lets there be a quick attraction between the 2 molecules, and sometimes that holds things together. If this is a maybe 12 carbon molecule, you're going to have bigger clouds and bigger attractions. You've actually run into these before when you dry things in the dryer. Say you throw a couple of big blankets into the dryer, you get basically static as you pull them out, and so the blankets temporarily stick together. If you let your laundry sit for a week, all that static will go away and they won't stick anymore, so it's temporary. So same thing here, if I put these 2 molecules into the dryer and they rub enough, they're going to stick, but eventually they'll fall apart. So if you can speed that up to maybe a nanosecond of stickiness, then you've got an understanding of our induced dipole. Next up is dipole-dipole attraction. So these are going to be a little bit stronger. They're not going to be purely accidents. And when I see dipole-dipole, I'm thinking of those polar molecules that we saw and reviewed from chapter 8. So the types of molecules that are involved here are going to be 2 polar molecules. It's an intermolecular force, so you always need at least 2 molecules. And what you'll see in these attractions is a dipole that gets attracted to another dipole. The arrow is the negative end, the plus is positive, and opposites attract, right? So we'll have those dipoles that are attracted to each other. And a simple example of this would be like 2 HF molecules. So I need to be able to identify that those HF molecules are lopsided where the electrons are near the fluorine, and then that those would line up. And here's my intermolecular forces or my dipole-dipole attraction. Because this isn't just temporary, this would be like you sit next to someone in class every day, and so you have more intermolecular force than just you bumping into a random stranger. So this is going to be a stronger attraction. All right. So if this is two strangers passing quick conversation and this is classmates, hydrogen bonding is even stronger. This might be someone that you take classes with for three or four semesters, and so you have an even stronger attraction or familiarity. So bonding, notice, is in quotes here because it's not really bonding, it's just an attraction between these particles, an intermolecular force. So don't get confused by that. What type of molecules are involved is a little bit more specific here. So first of all, we want to remember that hydrogen bonding is just a very strong version of dipole-dipole attractions. So I need two molecules with a dipole, but more specifically I need a donor and I need an acceptor. And so that donor is going to have a partial positive and that acceptor will have a partial negative. Those are little lowercase Greek deltas. The donor is going to have to be an OH, an NH, or an FH, and the acceptor will have to be an oxygen, nitrogen, or fluorine atom. Each of those atoms, even when they're in a bond, have lone pairs, and those are acceptor sites for those H's to come in and hydrogen bond. And those two are going to have strong attractions. So looking at the definition, those H's are highly polarized. That means they're very positive, not just a regular partial positive, but an extreme partial positive. And those opposite charges will be able to attract. So if I can draw you an example of this, rather than using the pink arrows, we're more likely to use partial charges. So I'm going to draw two water molecules. We're going to use that partial positive on the H donor, partial negative on the oxygen acceptor. With its lone pairs shown, that H will be able to be attracted to the opposite charge on the oxygen, and we just drew some intermolecular forces in there. The second lone pair could be a second place that another water could add on to that. So just recognize each lone pair as an acceptor place. So last of all, we're going to look at ion-dipole attractions, which are the strongest of the types of attractions we've seen. The name is self-explanatory. There's an ion with a whole charge and a dipole, which is a polar molecule. So grab that pink just to remind us it's got a molecular dipole. Opposite charges will attract. So here's a couple examples. This is like table salt dissolving in water. So the sodium ions are pulled out of the crystal by the oxygen in water, and the chloride ions are pulled out of their crystal by the hydrogens, which are partially positive in water. Just a reminder, water's polar, so it has a dipole, which is why it's part of these attractions. The negative oxygen is attracted to the positive sodium, and then here the positive hydrogen is attracted to the negative chloride. Just to color in those attractions, there's those ion-dipole attractions between the ion and the polar molecule. So just to review, we've gone from weak for all molecules up to the strongest here. You want to be able to look at a molecule and figure out what type of attractions it can participate in. And we will do some practice with that, looking at boiling points on the next slide.